Well, this podcast is about understanding empirical and molecular formulas. And the way in which we're going to do that is by using either a percent by mass or mass data. So first of all, let's back up and talk about what are empirical formulas versus molecular formulas. Let's start by looking at two simple compounds, the compounds of water and the compound of hydrogen peroxide. These two simple compounds have a different number of hydrogens and oxygens. One of them has both the same empirical and molecular formula, and one of the other compounds has the ability to have the ratio of the atoms reduced. Do you know which one is can be reduced? You guessed it. HO would be the empirical formula of hydrogen peroxide, while H2O2 is the molecular formula showing the exact number of atoms. Water, this is both the empirical and molecular formula. Now, when we go about figuring out formulas of compounds, we started this chapter naming them. And knowing the periodic table positions, etc., we could figure out some names of some compounds. Well, another approach to figuring out formulas is by collecting lab data and doing some series of calculations to figure out the formula. So, for example, here is one problem with lab data. I took this out of your book, and this problem has two elements in the compound. There's zinc in the compound and iodine in the compound. And what we know is that the mass of zinc is 2.5 grams and the mass of iodine is 9.7 grams. But we don't know the formula of the compound. Although I'm guessing that some of you might have a good idea if you know formula writing. But we'll come back to that. Let's say we have no clue what the formula of this compound is. What we can do to come up with a formula is these three steps. First, we're going to calculate the moles of zinc and calculate the moles of iodine. Second, we're going to look at the mole ratio, and that will allow us to write the formula. Okay? You know what? If you have an idea how to calculate the moles of zinc, given the grams, and how to calculate the moles of iodine, given the grams, pause the podcast right now. See if you can calculate that before I go to the next slide, because the answers are on the next slide. So pause it now if you have an idea, if you want to test your ability, and see how you do. All right, so let me cover up some of this. All right, so going from grams to moles is a matter of looking up the mass of a mole of zinc and using dimensional analysis to calculate the moles of zinc. Here we have 0.0382 moles of zinc and then 0.0764 moles of iodine using the mass from the periodic table of zinc and iodine. Now, if you look at those numbers, maybe you might see a connection between the two of them, maybe not. Whenever we're going to find a ratio, which is the next step here, once we find the moles, we want to find a ratio. We always want to do a ratio, so we have with a ratio that's a whole number, a number larger than 1. So when we do this ratio, we're going to put the larger number divided by the smaller number. Okay? And so if we do that, and we do a mole ratio, let's see here, how can I get this? There we go. Take the moles of iodine divided by the moles of zinc, do the math, 2-to-1 ratio, 2 iodine, 1 zinc. And you might say, well, why do we put the zinc first? Well, that goes back to formula writing. Put the metal ion, positive ion first, followed by the iodine. 2 iodine, 1 zinc, zinc iodide. Okay? So one method, as this points out, we start with grams. Let me summarize that. We started with grams. We went to moles using the periodic table. Then we calculated a mole ratio. And then we wrote the formula. The formula that we actually wrote would be called the empirical formula, the simplest ratio. And that's where we're going to, that's where we're working on right now, is the empirical formula. Now, in the next problem that we're going to do, we're going to actually add a step. And the new step that we're going to add precedes the grams, but then the rest of the process is the same. We're going to start with the percent by mass of each element in the compound, and then we're going to go to grams. And after we go to grams, we'll go to moles, mole ratio, and the empirical formula. Same process, now we're adding one more step. One more step. So here's the problem. The problem is that it's a compound that has 8.8% hydrogen, the rest is oxygen, and we're going to try to figure out if this compound is water. So we need to follow a few steps. I've outlined them here. If you want to think about this for a while first and see if you can do it on your own, great idea. Pause the podcast. Pause the podcast and then restart it once you've done your work. That's the best way to do a podcast. Stopping, pausing, seeing if you understand it, and then check the work next. All right, so I've shrunk it down so I have room to work. So first of all, if I have 5.88% hydrogen and the rest is oxygen, then how do I find the percent of oxygen? Well, if it's only hydrogen and oxygen, then really 100% is the sum of the hydrogen and oxygen. So the percent of oxygen I can find by subtracting, can't I? So 1, 4, that's the percent of oxygen. Yeah? So right now what we have is 5.88% hydrogen and 94.12% oxygen. And somehow or another we got to go from that to grams. And if we get the grams of oxygen and if we get the grams of hydrogen, then we can go to moles and do the same thing that we did in the previous problem. So all we have to do is figure out how to go from percents to grams. And it's easy if you assume that we have 100 grams of this compound. Always assume 100 grams, because guess what 94.12% of 100 is? Yeah, it's 94.12 grams. So now we know the grams of oxygen, and what's 5.88% of 100, but 5.88 grams. Yes? All right, so I'm going to go to a new slide here. So if I have 5.88 grams of hydrogen now, and let's just go down, 5.88 grams of hydrogen, and I have 94.12 grams of oxygen. Can I go to moles? Sure. I'm going to put that over 1. I'm going to look up the molar mass of hydrogen, which is 1 gram, that are in 1 mole. So that gives me 5.822 moles of hydrogen. And then I'll do the same thing with oxygen, over 1 times 1 mole of oxygen, 16.00 grams of oxygen. And I do that math, and I end up with 5.8, boy, these numbers look familiar, huh? Moles of oxygen. Aren't those essentially the same value? Aren't they essentially the same number? Yes, they are. But let me show you something. Bear with me for a moment. What if I wrote the formula of this compound this way? 5.822 and 5.88. Wouldn't that be a terrible formula to keep track of? Of course it is, because the ratios aren't simplified. But I suggest when you're doing these problems, you do it this way, because what that allows you to do is keep track of the moles. I look at these two, I want to simplify the ratio. 5.822 is smaller than 5.8, so I'm going to divide both of these by the same number. And when I divide 5.88 divided by 5.822, I get a subscript of 1 under the hydrogen, since that was the same number divided by itself, and the other value is essentially 1.01. Well, isn't that essentially 1? Yes. So, does that look like water is the question. Is this water? And the answer is no. Water is H2O. So this is not water. Not water. But what if I were to say that the molar mass of this compound is 34.02 grams per mole. And I wanted to know what is the molecular formula. Remember the other day when we did some problems, we noticed the connection in empirical and molecular formulas. Let me go back to this slide for a moment. We looked at empirical and molecular formulas, and we found that the connection between the empirical formula and the molecular formula, if we reduced the molecular to the empirical by 6, then the molecular formula weighs 6 times what the empirical formula does. So for this problem, if we want to figure out what the formula, the molecular formula of the compound is, then what we can do is figure out, well, what is the mass of HO? So 1 hydrogen, 1.01 grams, 1 oxygen, 16.00 grams. So HO has a mass of 17.01 grams. And if the substance that we're talking about has an empirical